Welcome to the deep dive. We take stacks of information and really try to unpack the key nuggets of knowledge for you. Today, we're setting our sights on a topic that's fascinated humanity for, well, forever: Mars. For millennia, Mars has been this canvas for our dreams, our fears, ancient myths, sci-fi fantasies, alien canals. But what we actually know now, thanks to decades of science and engineering, is frankly far more precise and maybe even more profound.
Oh, definitely. We're really at a pivotal moment, I think, in our relationship with the Red Planet. These robotic missions, they've given us this incredible portrait of a world that was once surprisingly Earth-like. Think liquid water, a thicker atmosphere, before it suffered this catastrophic climate collapse. So this isn't just, visiting another planet. It's a huge astrobiological question. And it's a case study with real relevance for Earth, too.
Right. So for this deep dive, our mission essentially is to explore three big pillars. First, what do we currently know about Mars from all this science? Second, the monumental journey we're planning to actually get humans there. The challenges are immense. And third, that ultimate, almost unimaginable ambition of, well, transforming the planet itself, terraforming. So get ready to have your perspective on our place in the cosmos, maybe expand it a bit.
Yeah, we'll be pulling together a vast amount of scientific data, engineering challenges, and honestly, some really profound ethical questions.
Yeah.
What's so fascinating here is watching how our understanding evolved from those first grainy images to, HD panoramas, and how all this knowledge now shapes the path forward for what might be humanity's biggest undertaking ever.
Yeah.
Setting up shop sustainably and responsibly on another world. Let's really unpack this.
Okay, so our journey to understanding Mars, it really kicks off with the robots, doesn't it? These robotic emissaries laid the groundwork over half a century.
Absolutely. That's the foundation. You can't even think about sending people without this vast repository of knowledge they've gathered. It's step one. Non-negotiable.
And it's such a fascinating story of discovery, kind of cyclical. Like, before we even sent spacecraft, you had people like Giovanni Schiaparelli back in 1877 seeing canali channels, and suddenly everyone's imagining intelligent Martian civilizations building canals.
Right. And that whole narrative just got completely shattered. July 15th, 1965, NASA's Mariner 4 does its flyby, sends back 21 images. And what do they show? A stark, cratered surface. Very moon-like, actually. That set a whole new paradigm, a much harsher one. Mars was cold, seemingly dead.
Talk about a reality check. Wow. And yet those early days of exploration were super difficult, weren't they? Something like, nearly 60% of missions failed in the first few decades?
Oh, incredibly tough. But breakthroughs still happened, even with the failures. You had the Soviet Union's Mars 3 managing a brief landing in '71. Just a glimpse, but still. And NASA's Mariner 9 became the first orbiter, also in '71. That's when we first mapped massive features like Olympus Mons and Valles Marineris, seeing the scale of the place.
And then came Viking in '76. That was huge, right? The landers.
Monumental.
Yeah.
Viking gave us the first color panoramas from the surface, and crucially, the first in situ life detection experiments, trying to find life right there. One of them, the labeled release experiment, actually showed results consistent with metabolic activity, like something was breathing or eating. But the other instruments found no organic molecules at all. So it left this huge question mark. Was it life? Was it weird chemistry? Tantalizingly ambiguous.
And that ambiguity kept the mystery alive, didn't it? For decades. Then jump forward to 1997, Mars Pathfinder. That mission was cool, used those airbags to bounce down, and it had the little Sojourner rover, the very first robotic vehicle to actually drive around on Mars.
Exactly.
Yeah.
Sojourner really proved the value of mobility. Being able to go look at different rocks, different places, which led directly, strategically, to the whole follow the water strategy. That became the mantra.
Yes, follow the water. And the Mars exploration rovers, Spirit and Opportunity, landing in 2004. They were the embodiment of that, right?
They absolutely were. And they hit the jackpot, especially Opportunity. Opportunity found layered sedimentary rocks, rocks laid down in water. And those famous blueberries, little hematite concretions that form in water. It was conclusive proof. Parts of Mars were once soaked in liquid water. Not just a little, but soaked.
That completely overturned the old cold, dead world idea from Mariner 4, didn't it?
Utterly.
And then Phoenix in 2008 went to the Arctic region and actually dug down and touched water ice, just beneath the surface.
Confirmed it directly, scraped it, saw it sublimate.
So the big question shifted again. It wasn't, was there water anymore? It became, okay, if there was water, was Mars habitable? And did life ever actually get started there?
Precisely. And that scientific agenda, that search for past habitability in life, has shaped pretty much every mission since. It's worth maybe just quickly running through the highlights again, showing that progression. You had Mariner 4 in 64, first close-ups, killed the canal myth. Mariner 9 in 71, first orbiter, showed us the huge volcanoes and canyons. Viking 1 and 2 in 75, first big surface science, but that ambiguous life search. Pathfinder and Sojourner in 96, showing low-cost landing and the power of rovers. Then Spirit and Opportunity in 03, boom, conclusive evidence of past water. Phoenix in 07, confirms the water ice up north. Then Curiosity, the Mars Science Laboratory, lands in 2011, confirms Gale Crater had a long-lived freshwater lake, conditions totally suitable for life. And that leads us right up to Perseverance and Ingenuity in 2020. Now, directly looking for signs of ancient life, and crucially, grabbing samples to bring home. Oh, and Ingenuity, first powered flight on another planet. We have to mention that. Which brings us pretty much to today's amazing robotic fleet. It really is like an armada up there and on the ground now. It is. You've got orbiters doing incredible work. MRO, the Mars Reconnaissance Orbiter, giving us those super high-res images, vital for picking landing sites. AMIEN is studying how Mars lost its atmosphere to the solar wind. Critical piece of the climate puzzle. Then there's the European Space Agency's TGO, the Trace Gas Orbiter, sniffing for methane, which could be a biosignature, though we don't know for sure. And they're working alongside veterans like Mars Odyssey and Mars Express, plus newcomers from the UAE, the Hope Orbiter, and China's Tianwen-1 mission, which included an orbiter and a rover. There's scouts, weather stations, communication relays, a whole network.
And on the surface, Curiosity just keeps going in Gale Crater, confirming that past habitability, finding that ancient freshwater lake environment, finding the key chemical ingredients for life. That was huge.
Absolutely massive. And Perseverance is building directly on that foundation. But in Jezero Crater, which we think was a river delta billions of years ago, it has an even more direct astrobiological goal, actively seeking biosignatures, signs of past life, and, maybe the most important part, collecting and caching those rock and soil samples for a future mission to bring back to Earth.
Okay, this is where it gets really interesting for me. Perseverance didn't just land itself. It brought Ingenuity, the little helicopter. It was tiny, right? Like less than 2 kilograms.
Just 1.8 kilograms, yeah. It was designed as a technology demonstration. Just 5 test flights planned, basically to see if flight was even possible in that thin atmosphere.
And it ended up doing what, 72 flights?
72 flights over nearly 3 years. It was unbelievable. It didn't just prove powered flight was possible, it aced it.
That's just a total game changer for exploration, isn't it?
Oh, completely. It went from tech demo to operational aerial scout. It started mapping terrain ahead of Perseverance, scouting routes, looking into areas the rover couldn't reach. This whole model orbiter providing context, helicopter, scouting ahead, rover doing detailed ground analysis. It's incredibly powerful. We'll see more of this. And like you mentioned, it's not just NASA anymore. China landing their Zhurong rover in 2021. It really signals this is becoming a global endeavor now.
So all this amazing data from all these missions, it paints this really vivid picture. Not just a world that had water, but like you said earlier, a world that kind of died.
Precisely. Yeah. Mars's geology tells that story very clearly. You see signs of a once active interior. Olympus Mons, the biggest volcano in the whole solar system. Valles Marineris, that canyon system that dwarfs the Grand Canyon. These tell you Mars had heat, had geological activity, and we know it even had a global magnetic field early on, just like Earth. That field would have acted like a shield, protecting its young atmosphere.
But the AVEN mission, the one studying atmospheric loss, showed us how that protection disappeared, right?
Exactly. As Mars's small core cooled down faster than Earth's, its internal dynamo, the thing generating the magnetic field, just shut down. And without that shield, the solar wind, this constant stream of charged particles from the sun, just started stripping away the atmosphere over billions of years. Surface pressure plummeted. The planet cooled dramatically. It led to this planet-wide climate collapse. Water couldn't stay liquid on the surface anymore.
Wow. But the evidence for that earlier, wetter past, is just overwhelming now, isn't it?
Undeniable. We see dried-up river networks, branching valleys that look just like river systems on Earth. We see deltas where rivers flowed into ancient lakes, like in Jezero Crater where Perseverance is, lake beds, sedimentary rocks formed in water, and specific mineral sulfates, clays that only form in the presence of water. Perseverance's samples are even showing multiple episodes of water interacting with the rocks. And of course, those vast deposits of subsurface water ice that Phoenix confirmed and orbiters have mapped. There's a lot of water still there, just frozen.
So the scientific consensus is really clear then. For a good chunk of its early history, Mars had everything needed for life as we know it. Persistent liquid water, energy sources, and the basic chemical building blocks, organic molecules.
All the ingredients were there.
Yes. So the billion-dollar question, maybe $1 trillion. Did life actually arise there? And that brings us back to astrobiology and the absolute necessity of Mars sample return.
That's the crux of it. The search for biosignatures, definitive proof of past or present life, is on. But it's tricky. Take methane. Curiosity has detected puffs of it. TGO is mapping it from orbit. On Earth, most methane is made by microbes, so super intriguing.
Yeah.
But methane can also be produced by geological processes, water interacting with rock. So finding methane isn't proof of life by itself. It's ambiguous.
And Perseverance is our most direct search yet, right? Looking for more complex signs.
It is. It's analyzing rocks in fine detail. It found volcanic rocks that were clearly altered by water over long periods. And it's found sedimentary rocks, like mudstones, rich in clays and sulfates, exactly the kinds of rocks that are really good at preserving organic molecules if they were there. It's even detected various types of organic molecules in things like manganese hydroxide, which on Earth is often linked to microbial activity helping to concentrate it.
But still no smoking gun.
Not yet. And here's the critical point where the scientific community has really come together. The consensus is that definitively answering the life question yes or no is probably too complex for a robot to do alone on Mars. Our rover instruments are amazing, but they're limited in scope compared to labs here on Earth.
Right, which is why we need to bring the samples back. Mars Sample Return, MSR.
Exactly. This huge multi-stage endeavor, primarily led by NASA and ESA, the European Space Agency, Perseverance is doing the first leg right now, carefully selecting diverse samples, documenting exactly where they came from, sealing them in super clean tubes. It's collected over 24 samples already as of mid-2025. Some it's dropped in a cache on the surface as a backup, others it's carrying with it.
This sounds like the most complex interplanetary relay race ever conceived.
That's a great way to put it. It really is. The current plan involves sending a lander to pick up those tubes. That lander will have a small rocket, a Mars Ascent Vehicle, or MAV, to launch the sample container into Mars orbit. Then, another spacecraft sent from Earth will rendezvous with that container in Mars orbit, capture it, and bring it all the way back home, probably landing sometime in the early to mid-2030s. It's basically the culmination of everything we've learned over 50 years of exploring Mars. It's us admitting, okay, we've pushed remote science about as far as we can. To answer the biggest questions, we need these samples back here.
And analyzing those samples in labs all over the world, that's going to tell us so much, isn't it? About Mars's evolution, its climate history, its potential for prebiotic chemistry.
All of that, yes. But the headline grabber, the reason it's so crucial, it's our best shot, maybe our only shot in the foreseeable future, to definitively answer that ultimate question. Are we alone in the solar system? Or at least, were we alone? Think about the implications. If we find definitive evidence of past or even present microbial life in those samples, it's a scientific and philosophical revolution. Changes everything. It would likely lead to a major pause, a moratorium on human activities on Mars, especially anything that could contaminate or harm that native life. Planetary protection becomes paramount. If the result is negative, if we find no signs of life after intensive study, that's also huge, though maybe less dramatic, it would likely shift the focus very strongly towards human settlement and making Mars a second home. So much hinges on what we find, or don't find, in those few dozen little tubes Perseverance is collecting. The whole future of our relationship with Mars, really.
Okay, so whether Mars has life or not, the next giant leap everyone talks about is sending humans. Moving from robots as our proxies to actually putting boots on the ground. But that's a whole different level of complexity, isn't it? What are the absolute core challenges when you switch from sending a 1-ton rover to sending fragile human beings?
Oh, the complexity just scales enormously. Orders of magnitude harder. The engineering challenges, the logistics, the sheer biology of keeping humans alive and healthy. It's all monumental.
Let's start with just getting there and landing. The tyranny of distance and gravity, as they say.
Right. First, the orbital mechanics. You can only launch efficiently from Earth to Mars in a specific window that opens up roughly every 26 months. The trip itself takes 6 to 9 months, depending on the trajectory. Then you'd likely stay on the surface for over a year, waiting for the planets to align again for the trip back. Then another 6 to 9 months home. So total mission duration. You're looking at 2 to 3 years away from Earth. That is a long time.
A very long time. And then there's the landing itself. EDL, entry, descent, and landing. NASA calls it the 7 minutes of terror. Why is landing on Mars so uniquely difficult?
It's that Martian atmosphere. It's less than 1% as thick as Earth's at the surface. That's thick enough to cause major heating as you plow into it in hypersonic speeds. Your heat shield has to work perfectly, but it's too thin to slow down a really heavy spacecraft using just parachutes, like we do landing capsules back on Earth. especially not something human-sized.
Right. So for the big rovers, Curiosity and Perseverance, NASA came up with that incredible sky crane maneuver, this rocket-powered backpack that hovered and lowered the rover gently on cables. Wild stuff.
Absolutely ingenious.
Yeah.
But that system maxed out at about 1 metric ton, the weight of those rovers. A human mission. You need to land maybe 50, even 100 metric tons per landing. You need habitats, life support systems, power generators, rovers, supplies, eventually the ascent vehicle to come home. Landing that kind of mass safely on Mars is, right now, an unsolved engineering problem. It's probably the biggest technical hurdle.
So how are we trying to solve it? What are the main approaches being worked on?
There were basically 2 main paths being actively pursued. One is developing much larger inflatable heat shields or decelerators. Think of a giant deployable umbrella that dramatically increases the surface area to catch that thin atmosphere. NASA's Loftide Experiment low Earth orbit flight test of an inflatable decelerator successfully demonstrated this technology in 2022. Scaled up, it could help slow down much heavier payloads.
Okay, inflatable heat shields, that's one path. What's the other?
The other, which has gained a lot of traction thanks to real-world flight data, is supersonic retropropulsion, or SRP.
Firing rocket engines forward into the direction of travel while you're still moving supersonically through the atmosphere.
Exactly. Using engine thrust to actively slow down rather than just relying on atmospheric drag. And the reason this looks so promising now is SpaceX. Their routine recovery of Falcon 9 first stages involves exactly this, using SRP to control their descent and land vertically. They've gathered an enormous amount of data on how rockets perform firing in those flight regimes. It's given a lot of confidence that this could work for landing very heavy things like Starship on Mars.
So mastering one or maybe both of these big inflatables or supersonic retropropulsion is absolutely critical before we can realistically talk about landing humans and habitats.
Absolutely critical. Without a reliable way to land tens of tons, human Mars missions remain purely theoretical.
Okay, so assuming we solve the landing problem, there seem to be 2 very different, almost competing philosophies or architectures emerging for how we actually do human Mars exploration.
That's right. And they reflect really different approaches and goals. It's fascinating to watch unfold.
First, there's the NASA approach, often called Moon to Mars. Tell us about that.
Yeah, NASA's strategy is very much an incremental one. It's government-led, focused on international collaboration, and it uses the moon strategically as a stepping stone, a proving ground for Mars technologies. The philosophy is, let's learn how to live and work sustainably on another world closer to home, the moon, before we tackle the much harder challenge of Mars. Build an experience, test the hardware.
And this relies on specific modular hardware components, right? The big SLS rocket, the Orion capsule.
Correct. The Space Launch System, SLS, is their super heavy lift rocket. Orion is the crew capsule designed for deep space missions beyond Earth orbit. And a key element is the Lunar Gateway, a small space station planned for orbit around the moon. It would serve as a staging post, a command center, a science lab, a place to assemble Mars vehicles.
So the Artemis program, NASA's current push to return humans to the moon, is essentially the blueprint for this Moon to Mars path.
Exactly. Artemis Asserts was the successful uncrewed test flight of SLS and Orion back in 2022. Flew around the moon and back. Artemis II, currently planned for maybe 2026, will do a similar flight, but with astronauts on board, the first humans to leave low Earth orbit since Apollo. And Artemis III, maybe mid-2027 or later, aims to actually land humans near the moon's south pole using a commercially developed human landing system, actually. SpaceX's Starship is currently selected for that first landing.
Interesting wrinkle there. So the idea is build up the gateway, establish a more permanent lunar base, test things like advanced spacesuits, closed-loop life support that recycles almost everything, maybe even nuclear fission power systems for surface power. All on the moon first.
Precisely. Prove it all out where help is only days away, not months. And do it with international partners through the Artemis Accords, these agreements setting principles for peaceful and cooperative space exploration. It's methodical, science-driven, builds capabilities step by step.
Okay, that's the NASA way. Then you have SpaceX, and their approach seems radically different. Direct to Mars.
Radically different, yes. SpaceX's vision is commercially driven, much more aggressive, and focused explicitly on enabling large-scale colonization, making humanity multiplanetary. Their core philosophy is achieving full and rapid reusability of their hardware to completely change the economics of space travel, making Mars potentially affordable for many. It's disruptive.
And their entire plan revolves around one single massive vehicle, Starship.
That's the key. Starship, paired with its super heavy booster, is designed from the ground up to be fully reusable, like an airplane. Land, refuel, fly again quickly. Starship itself is intended to be everything. The launch vehicle lifting off Earth, the in-space long-duration transport for the crew, the vehicle that actually lands vertically on Mars, and even the vehicle that launches off Mars to come home. One integrated system. It's designed to be the most powerful rocket ever built, capable of putting well over 100 metric tons into orbit and potentially that much payload all the way to Mars after refueling.
And their timeline is, well, let's just say ambitious. Sending uncrewed cargo starships to Mars maybe as early as 2026 or the 2029 window to start setting things up.
That's their stated goal. Pre-position habitats, power systems, ISRU equipment, the resource utilization stuff, sending cargo ships first, proving the landing works before they send any crew. Then crewed missions would follow.
And the absolute key enabling technology for SpaceX's whole Mars plan is orbital refueling.
Absolutely essential. The concept is launch a Starship destined for Mars into low Earth orbit, then launch multiple other Starships that are just tankers. These tankers rendezvous with the Mars-bound Starship in orbit and transfer propellant methane and liquid oxygen until its tanks are completely full for the long interplanetary burn. Without mastering orbital refueling on a massive scale, the Starship architecture for Mars doesn't work.
And the choice of methane as fuel is also crucial, isn't it? Because you can potentially make that on Mars.
Critically important. Raptor engines run on methane, CH4, and liquid oxygen, LOX. Mars has an atmosphere full of carbon dioxide, CO2, and plenty of water ice, H2O. Using processes like the Sabatier reaction and electrolysis, you can theoretically produce both methane and oxygen using Martian resources and solar or nuclear power. That's the core of ISRU in situ resource utilization. It means a Starship could land on Mars, refuel itself using local resources, and launch back to Earth. That's the key to making the whole system sustainable and lower cost in the long run. No need to lug all your return fuel with you.
So, okay, two very different paths. NASA, methodical, government-funded, international, science-focused, using the moon as a stepping stone, maybe more expensive permission initially. SpaceX, commercial, disruptive, colonization-focused, direct to Mars, betting everything on full reusability and ISRU. It really highlights these contrasting philosophies on how we should explore space.
It really does, and it raises fascinating questions about which approach or maybe some combination will ultimately get us there.
But amidst all this incredible hardware and rocketry, what about the humans? The crew themselves, they seem like potentially the most fragile part of the whole equation.
They absolutely are. That 2 to 3 year mission duration we talked about, inside a confined spacecraft, traveling millions of miles from home. The physiological and psychological toll is expected to be immense. We're still learning just how immense.
Let's talk physical threats first. Radiation seems like the big boogeyman of deep space travel.
It's arguably the biggest health risk, yes. Once you leave the protection of Earth's magnetic field, astronauts are constantly bombarded by two types of radiation. There are galactic cosmic rays, GCRs, high-energy particles from distant supernovae, constantly coming from all directions. And then there are solar particle events, SPEs, sudden bursts of radiation from the sun, which are unpredictable and can deliver a huge dose very quickly. Mars itself has basically no global magnetic field and a very thin atmosphere, so it offers very little protection on the surface either.
So how do you protect the crew? Lead shielding like in a dentist's office?
Not really feasible. Lead is way too heavy to launch in the quantities needed. The main approach is passive shielding, using the mass of the spacecraft itself. Things like water tanks, food supplies, equipment, even waste, can be strategically placed around crew quarters to absorb some of the radiation. On the surface, the best shield is simply dirt-burying habitats under several meters of Martian regolith. Active shielding, like generating an artificial magnetic field around the ship, that's still very much in the realm of science fiction for now, not practical with current tech.
Okay, radiation is huge. What about gravity, or the lack of it? We see astronauts on the ISS exercising constantly to combat muscle and bone loss.
Exactly. Zero gravity, or microgravity, takes a heavy toll. We know from ISS experience that astronauts experience significant bone density loss, muscle atrophy, shifts in body fluids, and even changes to their vision, something called spaceflight-associated neuroocular syndrome, or SANS. The big unknown is whether the partial gravity on Mars, which is only about 38% of Earth's gravity, is enough to prevent these effects, or allow astronauts to recover fully after the long transit. Maybe it is, maybe it isn't. We just don't have the data. Living long-term in partial gravity is completely uncharted territory.
Wow. Okay, so physical challenges are enormous. What about the psychological side? Being cooped up with a small group for 3 years, billions of miles from home.
Equally daunting, maybe even more so. Isolation, confinement, distance from Earth, the constant awareness of being in a hostile environment where a small mistake can be fatal. The psychological stressors are intense. There was a study called Mars 500 back in 2010-2011. It wasn't in space, it was a high-fidelity simulation here on Earth, where a crew of 6 lived sealed in a mock spacecraft for 520 days, the length of a round-trip Mars mission. Even in simulation, they saw significant issues: sleep disturbances, fatigue, increased conflicts, drops in performance, communication breakdowns. Now imagine that, but for real, with actual life or death stakes.
And add to that the communication lag, that delay, 4 minutes minimum, up to 24 minutes one way, depending on planetary alignment. That changes everything, doesn't it? No quick calls to Houston for help.
It's a fundamental shift in operations. You can't have ground control, micromanaging everything, or talking astronauts through procedures in real time like they do on the ISS. Mars missions will require deep crew autonomy. The astronauts themselves will have to be incredibly self-sufficient, cross-trained in multiple skills. They need to be able to diagnose and repair complex systems, perform advanced medical procedures on each other, make critical decisions sometimes instantly without waiting for guidance from Earth. The right stuff needed for Mars is going to be a whole different level of resilience, resourcefulness, and teamwork under pressure.
So, assuming they make it there, they land safely, that first Martian outpost, it's not going to be like a relaxed Antarctic science base, is it? It sounds more like setting up a demanding off-grid industrial plant just to survive.
That's a very accurate analogy. Forget leisurely exploration initially. The absolute immediate priority for the very first crews will be bootstrapping a self-sufficient foothold, and crucially, making sure they can get home. That means producing propellant.
Okay, habitats. What would those first Martian homes look like? Probably not geodesic domes with picture windows.
Probably not, at least not initially. Early habitats will likely be utilitarian, maybe inflatable modules that launch compressed and then expand on the surface. Or perhaps habitats integrated directly into the landing vehicle itself. And whatever they are, they'll almost certainly need to be covered with several meters of Martian soil, the regolith, for radiation shielding. That might be done by robotic excavators sent ahead of time, or maybe even 3D printing a shell using Martian soil right over the habitat modules. Concepts like that are being explored by groups like Foster Plus Partners.
Using lava tubes has also been suggested, right? Natural underground caves.
Yes, lava tubes are a really interesting possibility. If we can find accessible ones in the right locations, they could provide pre-made, large-volume shelters with built-in radiation protection. Definitely something future missions will scout for.
But the real key to staying there long-term, and especially to coming back, is this idea of ISRU in situ resource utilization, living off the land.
It's the cornerstone of any sustainable Mars presence. You simply cannot afford to launch everything you need from Earth. It's too expensive, the logistics are too complex, you have to learn to use what Mars offers.
And the two big resources everyone talks about are water ice and the atmosphere.
Exactly. We know there's abundant water ice just under the surface in many locations. Rovers and orbiters have confirmed it. You can mine that ice, melt it, and then use electrolysis running an electric current through it to split the water, H2O, into hydrogen, H2, and oxygen, O2. That gives you breathable air, drinking water, and rocket propellant components.
And the atmosphere itself, even though it's thin, it's mostly carbon dioxide.
Right, about 95% CO2. And that's incredibly valuable. NASA sent an experiment called EMO-XI, the Mars Oxygen In Situ Resource Utilization Experiment, on the Perseverance rover. And EMO-X has successfully, repeatedly, pulled in Martian air and produced pure oxygen from the CO2. It's a proof of concept, small scale, but it works.
So you take the oxygen from EMO-XI, combine it with hydrogen you get from splitting water ice, and you can make methane fuel and oxygen oxidizer for the return trip.
That's the plan. Industrial-scale chemical processing, right there on Mars. It allows you to generate the entire propellant load needed for the Mars Ascent Vehicle to launch the crew back into orbit for the journey home.
But doing all this mining ice, running electrolysis, running chemical plants like MOXIE, that takes a huge amount of power, doesn't it? And solar panels have issues on Mars with dust storms and the long nights.
Exactly. Power is a major bottleneck. While solar will play a role, especially early on, pretty much all serious concepts for a sustainable human outpost rely on nuclear-fission power systems. Compact reactors that can provide tens or hundreds of kilowatts of reliable power day and night, regardless of the weather. NASA is planning to demonstrate a full-scale fission surface power system on the Moon as part of the Artemis program, specifically to prove it out for Mars.
And life support, too, has to be incredibly efficient, right? Way beyond what the ISS does now.
A generational leap is needed. You need closed-loop systems that recycle close to 100% of air and water. Waste needs to be processed and reused. Food will need to be grown on-site, likely in hydroponic or aeroponic farms inside the habitats.
So those first Martian pioneers, they're not just going to be geologists and astronauts. They're going to be industrial engineers, chemical plant operators, nuclear technicians, power grid managers, high-tech farmers.
All of the above. As much as explorers, yes. Their day-to-day survival and their ticket home will literally depend on their ability to operate and maintain this complex industrial ecosystem, transforming the raw, dead materials of Mars into the essentials for life and transport.
Okay, this leads us into the really, really long-term, almost visionary stuff. Terraforming Mars. Taking that dead world and making it Earth-like. This always sounds like pure science fiction, but people are doing serious scientific inquiry into this now.
They are. It's moved beyond just sci-fi concepts into actual feasibility studies, modeling, looking at the physics and chemistry involved. Terraforming, by definition, means altering a planet's global environment, its atmosphere, temperature, surface water, to create a stable, self-sustaining ecosystem that's hospitable to Earth life, eventually maybe even humans, without needing spacesuits or habitats. The goal is to make the entire planet a habitable biosphere.
And achieving that requires 3 enormous changes, right? What are they?
That's the classical model, yes. First, you need to significantly thicken the atmosphere. Increase the atmospheric pressure. The initial goal is usually getting it above the Armstrong limit, about 6% of Earth's sea level pressure, which is the point where water can exist as a liquid on the surface, and where humans wouldn't need pressurized suits, just oxygen masks.
Oh.
Eventually, you'd want much higher pressure.
Okay, thicker atmosphere. What's second?
Second, you need to raise the global average temperature. Mars is frigid, averaging about negative 63 degrees Celsius, or negative 81 Fahrenheit. A thicker atmosphere, especially one rich in greenhouse gases, would naturally trap more heat and warm the planet. These first two are kind of synergistic. If you warm the planet, more frozen CO2, maybe from the polar caps or trapped in the soil, could vaporize, adding to the atmosphere and enhancing the greenhouse effect, causing more warming. A potential feedback loop.
Makes sense. Thicker air, warmer temperatures. What's the third step?
Third is establishing a stable hydrosphere and biosphere, reintroducing large bodies of liquid water, rivers, lakes, maybe even small oceans, and then seeding the planet with life, starting with hardy microbes, perhaps genetically engineered, then moving up to lichens, mosses, eventually maybe complex plants. The goal here is not just life, but life that performs ecosystem services, like producing oxygen through photosynthesis, eventually creating a breathable atmosphere.
The motivations behind wanting to do something so incredibly ambitious, they must be pretty profound.
Oh, absolutely. They range quite a bit. For some proponents, like Elon Musk is famously vocal about, it's seen as a pragmatic imperative for the long-term survival of the human species, a lifeboat, a backup planet in case something catastrophic happens to Earth. Others frame it more as a moral obligation, almost a destiny, for life to expand beyond its home world, to propagate consciousness into the cosmos. You even hear arguments that it could be seen as an act of restoration, bringing a world that we know was once habitable back to life.
But the sheer feasibility, that's where the debate gets really intense, right? What did the classical terraforming ideas involve?
The traditional approach, popularized by scientists like Carl Sagan and Chris McKay decades ago, really focused on releasing the carbon dioxide we know is locked up on Mars, primarily in the polar ice caps, which are mostly water ice but have CO2 ice too, and potentially absorbed in the Martian soil, the regolith. The thinking was, if you could just warm the planet enough to vaporize this stored CO2, you could kickstart that greenhouse effect we talked about. Ideas included things like building giant orbital mirrors to focus sunlight onto the poles, or perhaps dispersing dark dust to lower their reflectivity and absorb more heat, or even crashing asteroids into Mars for heat and volatiles. Factory production of potent greenhouse gases on Mars was also proposed.
Oh, okay, so vaporize the existing CO2. But didn't more recent studies, using much better data from all our orbiters, kind of throw cold water on that idea?
They really did. This has been a major challenge to the classical model. A very comprehensive study, sponsored by NASA and published around 2018, used decades of spacecraft data, MRO, Mars Express, MAVI, ANA, to really quantify how much CO2 is actually accessible on Mars, meaning CO2 that could realistically be vaporized and put back into the atmosphere using foreseeable technology. And the conclusion was stark. There simply isn't enough accessible CO2 left on Mars to thicken the atmosphere significantly. Even if you could somehow release all the CO2 from the polar caps and what's likely trapped in the upper layers of soil, The study calculated it would only get you to maybe 7% of Earth's atmospheric pressure. That's barely above the Armstrong limit and far, far short of what you'd need for significant warming or a breathable atmosphere. So
Yeah.
that traditional path, it looks like it's likely impossible with Mars's own resources and near-future tech.
Wow. So if Mars itself doesn't have enough ingredients, does that mean terraforming is dead? Or does it just mean we need to think about it completely differently? Like, it's not a resource problem, it's a technology problem.
That's exactly the pivot in thinking. The new paradigm, if you will, shifts the focus away from just releasing what's already there and towards actively manufacturing and deploying materials on a planetary scale to create the desired effects. So instead of just relying on CO2, maybe you manufacture incredibly potent artificial greenhouse gases. Things like perfluorocarbons, PFCs, these molecules are thousands of times more effective at trapping heat than CO2. Of course, producing and releasing the vast quantities needed would require a truly colossal industrial effort on Mars, far beyond just making rocket fuel.
Or some even more out there ideas I've heard about, like nanotechnology.
Yeah, there are some highly speculative concepts, like manufacturing and dispersing conductive nanorods made from Martian minerals into the atmosphere. The idea is these would absorb solar energy very efficiently and re-radiate it as heat. Some theoretical papers claim this could be thousands of times more effective per unit mass than even PFCs. Still very theoretical, though. Other ideas are more localized, like laying down large sheets of silica aerogel, this incredibly lightweight, insulating material over certain areas. This could trap heat underneath, potentially creating localized warm spots where liquid water could exist and microbes could potentially thrive even under the current thin atmosphere. Kind of like building planetary-scale greenhouses.
But even if you could thicken the atmosphere and warm the planet somehow, you still have that fundamental problem. Mars lost its magnetic field. Wouldn't the solar wind just strip away any new atmosphere you create?
That is the other huge, maybe even bigger long-term challenge. Without a protective magnetosphere, any thickened atmosphere would be vulnerable to erosion by the solar wind over geological timescales, maybe tens or hundreds of billions of years. Faster if there are big solar storms.
So some proposals actually talk about creating an artificial magnetosphere for Mars. That sounds like pure sci-fi.
It does. The most common concept involves placing a giant superconducting magnetic coil in space out at the L1 Lagrange point between Mars and the Sun. This coil would generate a magnetic field powerful enough to deflect the bulk of the solar wind before it even reaches Mars. Technically, the physics isn't impossible, but the scale is just staggering. Building and maintaining a superconducting structure that large, in space, powered indefinitely. We're talking very far future technology. It's highly speculative. Technology readiness is level 1, maybe 2, just basic concept stage.
So the takeaway here is, traditional terraforming using just Mars's resources looks unlikely. But if we develop truly revolutionary technologies for energy generation and material science, maybe manufacturing an atmosphere and a magnetic shield isn't physically impossible, just monumentally difficult and centuries away.
That seems to be the current thinking among researchers exploring these far future concepts. It reframes it. It's less about, does Mars have enough stuff? And more about, can humanity develop the technology and muster the truly astronomical amounts of energy required? We're talking energy requirements measured in terawatts, potentially comparable to Earth's entire current energy production sustained for decades or centuries just to initiate these processes. It's monumental. But it shifts the debate to technology and energy pathways.
Given that mind-boggling scale, maybe a more realistic approach, at least for the next few centuries, is phased, not trying to do the whole planet at once.
Absolutely. Most serious discussions now focus on gradual, multi-generational approaches, often starting with something called paraterraforming, or building world houses. This means constructing very large, enclosed, self-contained biospheres on the Martian surface. Think giant domes or covered canyons, inside which you can maintain an Earth-like atmosphere, pressure, and temperature, allowing people to live and work in shirt sleeves within those enclosed areas. You terraform regions, not the whole planet initially.
And then maybe a slow expansion from there. I've seen proposals outlining overlapping phases for planetary scale changes.
Yes, a common model looks something like this. Phase 1, abiotic climate engineering. This focuses on localized warming first, maybe using those silica aerogel patches we talked about, or small orbital mirrors focused on specific areas to melt subsurface ice and create small, protected oases of liquid water, preparing the ground, literally.
Okay, create some warm, wet spots. Phase 2.
Phase 2, introduction of pioneer species. Once you have stable liquid water and the slightly warmer temperatures in those protected zones, you start introducing life, but not complex life yet. You'd likely start with genetically engineered extremophile microbes, bacteria and archaea designed to survive the still harsh Martian conditions outside the initial oases. Their job would be to begin processing the Martian soil, maybe detoxifying perchlorates, fixing nitrogen from the atmosphere if you had some, and crucially starting photosynthesis to produce the very first traces of free oxygen.
So using biology to start changing the chemistry. Then phase 3.
Phase 3. Building a complex biosphere. This is the very long-term game. Gradually expanding those biologically active zones, introducing increasingly complex life forms, lichens, mosses, maybe eventually hardy plants as conditions allow. These organisms would slowly, over centuries or millennia, continue to alter the soil, increase the atmospheric pressure through processes like outgassing, and pump out more oxygen. The eventual goal might be to reach an oxygen level of maybe 100 millibars, about half of Earth's partial pressure of oxygen, but potentially breathable by humans without full pressure suits, maybe just needing supplemental oxygen.
This whole discussion, from ISRU to full terraforming, it brings us squarely to the ultimate ethical dilemmas, doesn't it? It's not just about what we can technically do, but what we should do.
Absolutely crucial. And the conversation is evolving. The established framework we've operated under for decades is planetary protection. This has two main components: preventing forward contamination, making sure we don't accidentally send Earth microbes to Mars that can harm any potential Martian ecosystem, or, critically, interfere with our scientific search for native life. We want to find Martian life, not Earth life we brought with us. And also preventing backward contamination, ensuring that if we bring samples back from Mars, like with MSR, or eventually astronauts, we don't accidentally introduce potentially harmful Martian organisms, if they exist, into Earth's biosphere. It's primarily about protecting the science and protecting Earth.
But the terraforming debate goes way beyond just protecting the science, doesn't it? If there is native Martian life, even just microbes, what moral status does it have? Carl Sagan famously pondered this.
He did. His famous quote, "If there is life on Mars, Mars then belongs to the Martians, even if the Martians are only microbes." That encapsulates the preservationist viewpoint. Proponents of this view argue that any independent origin of life, separate from Earth's, is scientifically and perhaps intrinsically invaluable. Its preservation, they argue, should supersede human desires for settlement or large-scale environmental modification like terraforming. Some even suggest we might have a duty to nurture Martian life if it exists for its own sake.
And the opposing viewpoint, the one that argues for human expansion.
That's often termed the anthropocentric or utilitarian view, strongly championed by people like Robert Zubrin, founder of the Mars Society. This perspective argues that humanity's survival, expansion, and the propagation of Earth's complex biosphere represent a higher moral imperative. From this viewpoint, microbial life, especially if it has an evolved complexity over billions of years, simply has less value than securing a second home for humanity and the rich tapestry of Earth life. In this view, terraforming isn't destruction. It's a creative act, bringing life and complexity to a largely barren world. It's about making Mars live.
Two very different ethical frameworks. But recently, there's been a third layer of critique emerging, hasn't there? Questioning the very language we use.
Yes, and this is really important. Scholars, particularly from humanities disciplines and indigenous studies, are increasingly challenging the terminology of colonization and settlement that's often used in space exploration discourse. They warn about the dangers of astrocolonialism, repeating the damaging historical patterns of earthly colonialism with its exploitation, displacement, and disregard for the other, whether that other is a native ecosystem or different human groups.
So it's pushing us to think not just about what we'll do on Mars, but who we will be when we get there, what values will guide us.
Exactly. It calls for maybe a decolonized approach to space, thinking in terms of establishing relationships, showing respect, acting more like a guest on another world rather than conquerors or owners. It adds a crucial layer of self-reflection to the whole endeavor.
Wow. Okay, what an incredible deep dive into Mars, from its deep past through our robotic exploration to these really profound questions about our human future there.
It really covers the gamut, doesn't it?
Yeah.
We've seen how our scientific understanding has matured, revealing this complex world that was once habitable, but then suffered this global climate catastrophe, a cautionary tale, perhaps.
And that hard-won knowledge is directly fueling the next great leap, actually sending human explorers. We see these two powerful, competing architectures, NASA's methodical moon to Mars and SpaceX's disruptive direct approach, both in active development.
Right. And the challenges are immense. Landing those heavy payloads, keeping humans healthy through years of radiation and microgravity, the psychological stresses. But these are problems being actively tackled by engineers and scientists right now. Solutions are being worked on.
And then looking further out, that long-term transformative vision of terraforming, what was once pure sci-fi is now subject to serious scientific analysis, even if the traditional methods seem infeasible with current tech.
New research into advanced materials, manufacturing potent greenhouse gases, maybe even artificial magnetospheres, offers a potential, albeit very distant, path forward. It keeps the dream alive, but pushes it into a realm of needing major technological breakthroughs.
But that ultimate ambition carries the ultimate ethical weight, doesn't it?
Absolutely. It's forcing this urgent, expanding debate, moving beyond just the technical aspects of planetary protection into deeper questions about the moral status of potential alien life, however simple, and crucially, prompting a critical examination of the colonial frameworks and language that have often shaped human expansion in the past. It really makes you pause and think about humanity's role and responsibility as we move out into the cosmos.
So wrapping this all up, what does this mean for you, our listener, and for humanity's path forward with Mars? Are there key takeaways or recommendations emerging from all this?
I think there are some clear priorities that emerge from the science and the planning. In the near term, number one has to be fully fund and prioritize Mars sample return. What we learn from those samples will fundamentally shape all future human mission plans and ethical considerations. It's that important. Number two, aggressively accelerate and diversify the development of entry, descent, and landing technologies. We need robust ways to land heavy payloads. That means pushing forward on both inflatable decelerators and supersonic retropropulsion. Landing is the gatekeeper, also critical. Expand human analog studies, like Mars 500, and research into the physiological effects of deep space radiation, partial gravity, psychology leveraging platforms like the Lunar Gateway as they come online. We need better countermeasures. And finally, proactively work to harmonize international ethical and legal frameworks for Mars before major settlement activities begin. We need consensus on the rules of the road.
Okay, those are near-term priorities. What about the long-term vision?
Long-term, the focus has to be on enabling a sustainable presence. That means sustained investment in foundational research for in situ resource utilization ISRU. Getting really good at making water, air, fuel, building materials from Martian resources. That's the key to breaking dependence on Earth. And even though full terraforming is distant, we should support the foundational science into those more promising future technologies, things like advanced atmospheric warming materials, maybe artificial magnetospheres. This isn't just for Mars. This kind of fundamental research could potentially have spin-offs for understanding and managing Earth's climate, too.
And perhaps overarching all of this, that ethical dimension we discussed.
Absolutely. Foster truly interdisciplinary dialogue on the ethics of settlement and potential terraforming. This can't just be engineers and scientists talking to each other. We need to formally integrate ethicists, sociologists, legal scholars, historians, and diverse cultural perspectives, including indigenous voices, right into the mission planning process from the early stages. It's absolutely crucial that our expansion into the solar system is not only technologically brilliant, but also ethically considered, responsible, equitable, and ultimately sustainable for both humans and any potential other life we might encounter.
So this deep dive into Mars, it really does reveal not just the future of space exploration, but it holds up a mirror, asking us to reflect on the future of humanity itself.
Well said.
What stands out to you the most from exploring Mars with us today? As you think about it, maybe ponder this. If we do discover life on Mars, even simple microbial life, how would that discovery fundamentally change your understanding of our place in the universe and maybe our responsibilities toward other worlds? Something profound to think about until our next deep dive.